Okay, maybe let's start. So how did you find yesterday's lecture? It's very introductory, right? So today we will cover like more methodologies and all those kind of things. Yeah. So hopefully you will get some insights, and then you can try to apply similar approach into your research. Yeah. So yesterday, if you remember, like there were 4 lectures, right? 1, 2, 3 was by me and 4 was by Dr. Momita. So today I am going to cover lecture 5, 6 and some part of 9. Okay. The reason being actually 9 was about joint consideration of security and sustainability. So if we are going to cover already security, I thought I will cover briefly that part as well. Okay. We will come back again to that part, but briefly I will cover. Okay. So also I would say there is some change. Yeah. So lecture 7, that is about system design methodologies for sustainability, was today. Okay. But I am kind of moving it tomorrow. So everything about security today and everything about sustainability tomorrow. Yeah. So because initially I thought I will do security, sustainability, then do mix up. Yeah. So we will cover mainly security. That is why you can say from the outline is like system design methodologies for digital security 1, 2 and analyzing methodologies and joint considerations. Okay. Now you already have seen this. Yeah. What can be different categories of attacks on electronic devices. So I have brought it again just to tell, like we are going to cover some into this and we are going to cover some into this category again. Okay. Okay, so in the previous one you saw there was on the left hand side physical and side channel attack. Yeah. So it's not really getting the information directly, rather using some physical properties. Yeah. So how this is typically done? Yeah. So in typical scenarios you will see like you will have some input ciphertext, yeah, which means there is a text that is encrypted and it is sent. Yeah. And then you do the decryption at the receiving end and you get the plain text. Yeah. This is how it typically happens. But as part of side channel attack, so when the decryption is happening, you can try to extract some side channel information. Yeah. So like what is the power consumption? Yeah. What is the maybe electromagnetic radiation? What is the sound level? Yeah. And then you can analyze these information, and then from this also you can get the kind of encryption key. And if you get the encryption key, you can get the plain text as well. Okay. So this is how typically this side channel attack is done. Yeah. So main purpose is typically to find the key. Yeah. And like I have said, if you are encrypting with different keys, yeah, like maybe different length, and then your side channel information will vary. Yeah. There could be high power label, low power label and all those things. Okay. So this is how side channel analysis finds out the key, and then you can always get the plain text. So the left branch actually can also be called as like hardware level security attacks. So you see, like we are using some hardware properties, yeah, not really direct information. That is why some people categorize this as hardware level security attacks. And these ones are expected to rise in future, and mainly due to 2 factors. So the first factor I would say is hardware Trojan insertion. Yeah. So you see, like there are a lot of electronics manufactured. If someone wants to have attack on some system, like from one country to another country's system, engineers or someone from inside can insert hardware Trojans. Yeah. When things operate, they let the whole system down. Okay. And the main reason you can guess, it's due to excessive outsourcing in hardware supply chain. Yeah. So not everything is done at one place. So there are so many things manufactured at different places. Yeah. like CPU, GPU, memory, all different companies, and then it goes into one. Yeah. So if everything is at one place, it's much better. That is why you can also see lots of countries are trying to kind of secure supply chain. That means they want to manufacture just there, okay, not rely on outside world. Yeah. And if this kind of things happen, basically they can cause denial of service of various types. Yeah. So it's like whatever you want to do, you cannot do. So that's one of the factors. And the second one is the rapid increase in the number of connected devices. Yeah. So imagine if my laptop is not connected with internet, nobody can attack. Yeah. There could be physical tampering, they can do reverse engineering to get some information, but if it's not connected, nobody can log in. Yeah. Or nobody can put any virus or something. So because of the connectivity, we are facing all these issues. Yeah. So connectivity provides some advantage, but it leads to a lot of problems as well. Okay. What it does, so it makes it feasible to craft and insert malicious programs through various upgrades. Yeah. So like you can see sometimes you get notification like update is ready. Yeah, because it is connected. So when you do those upgrades, there could be some malicious program encapsulated into that update, and then they can start doing some denial of service or leaking some information. Okay. And these programs, I mean, typically you can say can leak physical attributes. Yeah, like again I said power, temperature, and they can do basically in a covert fashion. So it's like maybe the power label of my laptop is being sent, but I do not know. Yeah, because it's like at quite different frequency at which it is sent. So that is why it is called covert leak out. So nobody notice it. Okay. So these can be sent, and then attackers can use this to decode personal or national defense data. Yeah. So if it's like a kind of national defense system, those are the main targets. Yeah. So that can be very fatal. And if you are covertly leaking out physical attributes, this is called covert channel attack. Yeah. There is a covert way to transfer the physical attributes. That is why covert channel attack. Okay. Now let's look on covert channel a bit more. So what is the communication media typically in these? Yeah, we already have seen some. So there could be heat transfer. Yeah, so like temperature transfer from one place to another. If it is temperature, we call this thermal covert channel. Yeah, short form is TCC. Okay. Timing can be another communication media or another side channel property. Later on we are going to look each of these one by one. Yeah, how this thermal covert channel can be used, how the timing can be used, and it could be inaudible sound as well. Yeah. So for all these three, later on we are going to see how exactly the attack can happen. So again, inaudible sound is like it's being again covertly transmitted, but nobody can hear it because the frequency at which it is transmitted is inaudible. Yeah. Okay, I think I'm putting a question here again. So we have seen these communication medias, right? Can you think of any other communication media? I don't know if you get, again you can use your phone. Yeah. Let's see if it's working or not. I think I need to go there again. So it's not working, right? Just give me a second. Hopefully this one, yes, I think it's working. So any other communication media you can think apart from temperature, timing, inaudible sound? Anything you can think of? Okay, body language, that's interesting one. Okay, yeah, I think energy, yeah, energy can be another thing, like power, you can send the power level. Yeah, I think body language, yeah, can be interesting. Or you can also think like, you know, sometimes there are ways people can find out what exactly you are speaking, yeah, just by the lip movement or something. So it's kind of some kind of movement, yeah. But this needs to kind of we need to somehow relate with a computer, yeah. What could be the body language? Yeah. Okay, frequency can be one thing, yeah. Yeah, I think frequency can be another. I think frequency is also related to power. Yeah, you can say like if the processor or core is operating at certain frequency, it has some power level. Yeah, so they are related. Sign language. I'm not sure how to use it. I don't know if you can explain. Yeah, whoever typed it. Yeah. Maybe there is a way. Yeah. Okay, acoustic signals. Actually, acoustic is typically interchangeably used with sound, yeah. So it's the same. Okay, there are a few other ways like electromagnetic radiations, yeah. Each electronic has some radiation level, so that one can also be used. Okay, good. So you have some nice, interesting ideas. Okay. Okay, sorry, I think I need to log out this one and go there. Okay, so what are the advantages of covered channel? Yeah, you might have seen other attacks, but covered channel has some advantage over other ones. Okay, just give me a second. Okay, so they do not rely on shared resources, cache and memory. So if you can see, like there are lots of attacks that happen because there is a shared resource, yeah, but this one does not rely because it can secretly leak some physical attributes. Okay, and this also does in a wireless manner, yeah. So like I said, you covertly leak something and then nobody can notice. Okay, so this can be like dangerous, yeah, nobody can find it out. Okay, so now let's look, like I said, I will look one by one. So let's look first this hardware Trojan based attack. Okay, so in that we are going to look hardware Trojan assisted power budgeting system attack, and this power budgeting system attack is for many core systems. Okay, so you know, like to these days most of the processors are many cores, right, or multi cores. They're like 8, 10, 20 cores. Okay, so in that we can do something like power budgeting system attack or power budgeting attack with the help of hardware Trojans. Okay, so what is power budgeting in many core system? First let's look that. Okay, some kind of introductions of that. So like I said, this could be like a processor into your smartphone, like 8-core processor, yeah. So this is many core, means there are like 8 or 10 cores. Okay, so what is power budgeting here? So here all the cores from 1 to 8 are constantly competing for their shares of power out of the maximum power available for the chip. Yeah. So if you take a processor, it's kind of said what is the maximum power level. Yeah. So our phone has like around 10 watt, the CPUs in the laptop, they have like 20 watt, but desktop ones, they have like 65 watt, something like this. Yeah. So that is the maximum power available, but if you want to run something on each, so that 65 watt has to be shared amongst all these, right? But if you want to do something on any of the cores, it has to request like how much power it can get from that 65 watt. Okay. So this is like, this always happens in our processors. Okay. And to kind of find out how much exactly should be given to each core, there is typically a budgeting scheme. Yeah. So that efficiently allocate power to achieve the highest possible overall performance. Yeah. So even if like maybe this core is requesting I need 2 watt, but it might not get 2 watt. Yeah. It might get maybe even less, because other cores are going to give better performance overall. Okay. So this is like power budgeting. Okay. So now let's look some example. Yeah. So this is a 3x3 multi-core system or many-core system. Yeah. So what happens here? So when a core wants to run some applications, okay, let's say this core B, yeah, it wants to run some applications. So what it will do? So it's going to send a request to one of the cores that will act as a manager. Yeah, because out of all the systems there is one that is manager. Yeah, it's managing everything. So if core B wants to run something, it will send a request. So here let's say core A is the manager core, and this request will go in this form. Yeah, and then this manager core is going to return the power budget that it can use. Yeah, and power is directly related to frequency. Yeah, so you can say like if it says I want 1.2 watt, that is equivalent to 2 gigahertz. So the manager is going to kind of return a response to core B just to say you can run at 2 gigahertz. Yeah, but it might be it cannot get that much. Yeah, because other cores are also requesting. Okay. So here manager makes decision based on all the requests that are coming from all the different cores, and it makes the allocation in a way so that overall performance of the system is maximized. Okay. So this is how this happens in our processor as well. Yeah, there are so many cores, each of them need to run at certain frequency or power level. They all request based on what is on them, and then manager decides how much power can be given to different cores. Okay. So this is how power budgeting happens in many core systems, and this is one of the example.
So in real systems, are they working as like you have one manager and other like master slave, or they are working on some different mechanism?
Mostly it's like
core systems that are presently available.
Mostly it's like this. So there is a manager that manages everything. Yeah. So even like in our smartphone, yeah, there are like 8 cores. Yeah, but the operating system will be running on one of them. So it's not using all of them, or maybe 2 of them. Yeah, so, but typically it's one of them. So that core is like a manager. Yeah, the request goes to that, and then it decides. Yeah, so the manager core means simply it's not really the core, it's the kind of system that is running on that. Yeah, or the operating system that is running on that. Okay. Yeah. So this is happens in our laptop as well. Okay. Yeah, please feel free to ask questions, yeah, whenever you have any. Okay, so now let's look how a hardware Trojan assisted power budgeting attack can be done. Okay. So we have already seen this one, right? So this one is normal situation, there is no attack. So core B requests its power budget, and it goes to the manager A, and then it gets some kind of response. Yeah. So here it says you can run at 2 gigahertz. So this is the typical operation how things will be running, yeah. But let's say on core C, or there could be a router that connects core C, yeah, there is a kind of hardware Trojan, yeah. So what it can do, so basically when you make a request, it can simply change the request, yeah. So let's say it says I want 1.2 watt, but this Trojan changed the request to 0.1 watt. So the at the manager for this one, request will be for less watt, yeah, and because of that it will not say you can run at 2 gigahertz, it will say you need to run at 1 gigahertz, okay. So you can see, like, now whatever power it needs it cannot get, because there is a hardware Trojan in the middle that changes the requests, okay. So this is one example of hardware Trojan based attack, okay. And if this happens, you can simply say this results in denial of service attack, yeah. So like maybe it wanted to do some critical task, now it cannot get the frequency label or power label, so it cannot do with the same performance, yeah. And maybe if it's kind of a critical system like a car or something, so like you wanted to apply brake, and the brake control will run on one of the cores, yeah, and then maybe the moment you press the brake and the moment it really happens, it might be much delayed, yeah, okay. Later on we are going to see a bit more on this kind of examples, yeah, but simply I hope you get, yeah. So whenever some request goes from a core to the manager, if there is hardware Trojan in the middle, it can change the request, okay, and thus the core that is requesting, whatever it is requesting, it will not get what it wants, okay. It can be in real life as well, right? Like we sometimes request something from some places, right, but there are people in the middle, they can change it, yeah, and then you get different response, yeah. There could be people with malicious intention, yeah, okay. Okay, so there we saw there was one hardware Trojan, yeah. So now I just have put a question, what do you think can happen if there are multiple hardware Trojans? So let's say this is also kind of has hardware Trojan, and this one also has hardware Trojan. Okay, I think I need to, I don't think you can see, right, on the, let me go to that one. Okay. So what I mean, like, you know, with one hardware Trojan, the request was changed, right? But let's say there is hardware Trojan on second one as well. So what can potentially happen? Yeah, so the more cores will be affected, yeah. Anything else you can think? So multiple critical tasks delayed, yeah. So it's like if there is a request from multiple places and there are multiple Trojans, all of them will change your request, yeah. The first one maybe said 1.2 watt to 0.1 watt, yeah. But if there is Trojan here, this can change it further, yeah. It can say maybe again 0.1 to 0.01 watt. So the request can keep changing, yeah. So you can see this is kind of more problematic situation, yeah. Okay, multiple interrupt requests. Multiple Trojans can block the multiple communication ways and make system request completed, delayed or blocked, yeah. Behavior of the overall system would be more erratic, of course, yeah, like whatever system wants to do, you will never be able to achieve because always the requests are changing, okay, yeah. Short circuit, okay, I mean could be possible, yeah. So for example, let's say you requested 1.2 watt, right, and this whole chip has like 65 watt, right? Let's say you requested 1.2, but it gave you like maybe 20 watt, and then it can heat up too much. Yeah, it's like too much extra power. Yeah, so there could be short circuit. Yeah, that's possible. Yeah. Okay, good. Okay, let's see the next one. So we have seen this. Just give me a second. I think there's something wrong. Okay, so how now that can be detected, right? If you want to really stop, that has to be detected, right? So at the moment I would say do not look this part, yeah, just look on the left hand side. Okay, so let's say you had this 4 cores, yeah, A, B, C, D. This one requested 1.4 watt, this one 1.3, this one 1.2, this one requested 0.1, yeah. So this is like one approach. It can be how you can detect. So you can take average of all these, yeah, and then you can do some calculations like this. So like how much is the deviation from the average? Okay, so you can say average minus original request, yeah. So this is the original request. So for A it will be 0.9 watt, right, because average is 1 and request is 0.1. Similarly for B it will be minus 0.2. Okay, so these will be the kind of deviations, yeah. Now you can kind of develop some threshold. If you say if your deviation is more than certain value, you can say this is potentially an attack, yeah. So let's say greater than threshold, and this threshold can be 0.4 watt, and then you can say there is a hardware Trojan attack, yeah. So thresholding based mechanisms are always used, yeah, in a lot of places. So how this is how you can detect, yeah, but how you can stop it, yeah. So stopping is on this side. Now you know this core is infected, yeah. So now you can do another average, but do not take the power value of the infected core, yeah, because it has been reduced too much or it has been increased too much. Then you average only uninfected cores, yeah, and this average is 1.3 watt, and based on this average you can do another distribution, yeah. So you can see like this one was originally something, but it became infected, but then with some reset you can allocate higher, yeah. But when you do this average in the defense, do not take the power label or the request power label of the infected core. Okay, so this is one very simple, yeah, like thresholding mechanisms, yeah. Okay, all right. So this is this was developed by one of the PhD student in my group. I will tell you a bit more about the paper that it has, where it was published. Let me see. Again, I think I have some question after this. Okay, so thresholding was one method to detect it, right? So can you think of any other method? Any other idea you can think of to detect and then mitigate it? Yeah, so detection means you find the infected core, and mitigation means you correct its power level. Okay. Always maybe try to think from different places, yeah. Any ideas, anything you can think of? So I also have not thought yet. So I just want to discuss with you. Yeah, what's your thought? Limit the change in power request by setting a threshold. That's interesting one. So it's like when the requests are made, yeah, if it goes 0.1, it's obviously it is infected, but you can say no request can be less than 0.8 watt or something like that, yeah. So you can set the limit, yeah. So this one is kind of a direct defense, yeah. There is kind of you can say it's like security by design, yeah. So it's not letting that happen, but this is interesting one, yeah. Frequency behavior analysis, detection and mitigation. Okay. I think like we said, yeah, when the request is made, typically in return it is the frequency level, yeah. So of course that can be analyzed, and then it is sort of something similar, yeah. You have to say like if frequency level is kind of returned by the manager core is very, very low, there is potentially an attack, yeah. Okay. I think there could be few other things. So if you remember, like we were saying, there is a request going from different cores, right? So you can look like what is the load of the request, yeah. Maybe that core needs to run some very compute intensive application, yeah. That means it typically needs high frequencies or high power, yeah. There could be some core that doesn't need to run very compute intensive application, so its request can be low. So kind of the response that you get, you can always think of relating it to the workload that it wants to execute, yeah. If the difference is too much, yeah, like you are going to sacrifice too much in the performance, then you can kind of say potentially there is an attack, yeah. Okay. So it's like, for example, in you request maybe from a bank some ATM machine, yeah, some cash or something, yeah. If you get in return, like let's say 1000 you requested, but if you get 800, 900, maybe it says the machine has something wrong, you can say this is fine, yeah. But if you just get 100 rupees, then you can say potentially something has gone wrong, yeah. So it's like, what do you want if that differs too much based on what you get, yeah. Okay, that's good. Okay. So we have done this one. Okay. So now let's look some results, yeah, like what kind of things are impacted as a result of this hardware trojans present in the chip. So the first one, okay, so the first one is called something like infection rate, yeah. So like how many requests are infected, yeah. Let's say in the system, maybe over certain time when the applications are running, maybe 1 hour, the requests keep going to the manager, yeah, from all the cores. But then lots of requests are modified, yeah. So this can be said like infection rate, yeah. So if half of the requests are modified, you can say infection rate is 50%, yeah. So out of 100 requests, 50 are modified, okay. So this is something, one metric that can be used, yeah. So now let's look this infection rate with respect to the number of hardware trojans, yeah. So like in previously I said, yeah, if there is 1, if there is 2, if there is 4, yeah. So definitely that one is going to increase the infection rate, right? It's going to modify more and more requests, yeah. And after certain point, for this system that is 64 cores, yeah, or you can say 8 by 8, if you have like 10 hardware trojans out of 64, then around 50% of the requests will be modified, yeah, that means they are infected, okay. And here there is one more, there are like two plots, yeah, so you can see one is the global manager is in the center, yeah, so you can see we saw the manager was at one corner and request was going from another corner, but global manager can be in one corner, can be in the center as well, yeah. But you see, like if the global manager is in one corner, so the blue line, yeah, the infection rate will be more because it has to travel a lot, yeah. But if it is in the middle, the infection rate will be less, yeah, because it can request can reach to the global manager much faster, yeah. So imagine in that 3 by 3 system, yeah, if the global manager is not the top left but the middle one, yeah, so all the requests from different one are going just next to it, right, then there is no point, no place to kind of modify the request. So that is why you can see if it's in the corner, infection happens much more, but if it is in the center, infection happens less, okay. So this is with respect to a number of hardware trojans for a system of size 64, but you can also increase your system size, yeah, maybe it has 512 cores, yeah. So there are some processors in the market with thousands of cores, yeah. So in this one you will see like to reach the same infection label, you will need to have more hardware trojans, yeah. So for example, whatever you could achieve with 10 trojans here, you need maybe around like 30 trojans, yeah, because the system is much bigger, okay, yeah. Okay, after this I have a question. So what do you think of the placement of hardware trojans, whether it's going to impact the infection rate or not? So you know the hardware trojan again can be in the middle, can be somewhere, right? So whether it's going to impact the infection rate or not? I think I have a question slide, yeah, let me try to go there. No, not this one, sorry. I think it will not run like that one. So just a simple question is, do you think placement of hardware trojans will impact infection rate? Yeah. So like placement of the global manager, yeah, where all the requests are sent, it changes the infection rate, right? Similarly, hardware trojans can be at different places, yeah. So do you think that one will also change the infection rate? I would say yes, yeah, because again like global manager, if where exactly is this one, if lots of requests are passing through that, then it will change much more, yeah, but if less requests are passing through it, it will change less, okay, yeah. So I think my next question is around that line. Okay, so let's say these trojans are around the center, yeah, maybe 2, 3 or 10 of them, and they can be distributed randomly in the whole chip, yeah, or they can be in one of the corners, yeah. Let's say the 64 cores, yeah, 8 by 8. So in one of them everything is around the center, yeah, maybe 10 cores in the center are infected, and then in another one all these 10 can be distributed, yeah, and in another all these can be in one corner on the left hand side, top left or top right, yeah. So what do you think will be the kind of value of infection rate? So in which case do you think it will be highest, or in which case do you think it will be the lowest? Yeah. So if you can say in this case infection rate will be highest, and in that one, in another one, which one infection rate will be the lowest. Anything typed? Oh, it's not yet here. Okay. Maybe some internet issue, I don't know. Did you type? Some of you typed? No. Maybe internet is not working very well. Okay, let me ask in a different way. Yeah. So let's say if all the hardware trojans are in one corner. Yeah. So do you think infection rate will be highest or lowest? It should be lowest, right? Yeah. So which one will be highest? In center one, yeah. Because typically all the request has to go through the center. Okay. Yeah. So now you can think of like you want to attack a system, yeah, that has many cores, yeah. So you know like where exactly to plant these hardware trojans to have the maximum impact. Okay. All right. Now let's see some comparison results. It's very slow. Some performance issue with my laptop. Okay. So infection rate comparison, yeah. Like I said, hardware trojans are around the center and they are distributed randomly and they are in one corner, yeah. So let's now first look one system, yeah, this 64 cores, okay. What will be the infection rate? Yeah, like you already can guess, if hardware trojans are in the center, that will be highest, yeah, and if they are in one corner, that will be the lowest. Okay, in randomly distributed, it will be somewhere in the middle. Okay, now here is the different system, yeah, but there is kind of to have more and more results. So this A represents a case where out of 16 cores, one of the core is infected with hardware trojans, yeah. So 1 by 16, yeah. So if it is 64, that means 4 hardware trojans are there, yeah. If it is 128, so you can simply divide 128 by 16, so that many hardware trojans, yeah. So that is why you can see maybe this graph is more or less the same, yeah, because as the number of cores are increasing, the number of hardware trojans are also increasing. Okay. In the second one, so here 1 core out of the 16 is infected, here 1 out of 8 is infected, yeah. So you can see the number of hardware trojans or infected cores are double, yeah. That is why you can see the infection rate here is this much, but here it's very high, okay, because the number of hardware trojans are just double, okay. So the infection rate, you can't say it's exactly double, but more or less much higher, okay. But this trend is always there, okay. All right. So hopefully now you know if you want to attack a system that has multiple chips, this is how you do, okay. Or think of another system like a data center, yeah. So again, when there are a lot of servers in the data center, there is a topology that is followed to connect them, yeah. So again, if you want to let the whole system down, you have to think you should attack something from where lots of information is flowing, yeah, not something in the corner, yeah. If you can attack something that is on more centralized position, that will have more impact, okay. And I think yesterday I told you, like, if you want to be the best security expert, develop the best defense mechanisms, it's best you be the best attacker first, yeah. So think of attacking the systems in all the possible ways, yeah. And this is how a lot of companies do, yeah. These security companies, they have a lot of attackers, so they keep attacking systems and I mean, it's kind of in an ethical way they do. They don't harm anybody from the companies, but then they develop the defense based on what they think all the possible attacks can happen. Okay. Okay. Now let's look another metric, like applications performance changes. Yeah. So because a request is going, yeah, from one core to the manager, and then it is getting modified, yeah. So in this case, we are assuming like there are two attackers. That means two hardware trojans, yeah. And then that means there will be, and there are two victims, yeah. So like two cores are requesting, yeah, and there are two trojans present. Okay. So here what will happen, like the victim cores, like you have seen, their power request is reduced, yeah, typically. So those victim cores will have reduced performance, yeah. And this, as there is more and more infection, their performance will keep decreasing, yeah. But these attackers, the trojans, they can, for their own request, they can always ask for more power, yeah. So they can boost their own performance, yeah. So this is just to create some kind of disturbance in the system, okay. Similarly, this is another scenario. So here we took some kind of mixture of some applications from some benchmarks. Here is another mixture of application, just to kind of show it works with all the applications, yeah. So mixture means there are lots of applications running on one core, core 2, core 3, core 4, like that, yeah. And out of that, two of them, we are assuming there is hardware trojan, and two of them are making the request to the manager, okay. So this is how the performance will change, yeah, okay. Okay, hopefully it's clear, yeah. Okay, now I have a question, yeah. So will there be impact on other metrics than performance? So PC performance, right, it reduces, yeah, of typically the victim applications or victim cores, yeah. So can you think of any other metric that will also be impacted, yeah. It might be basically increasing in value with the hardware trojans, yeah, or it can basically reduce, yeah. I don't know if you can see the screen. No, you see the previous one, right? I think from PowerPoint it's not working. Let's go next one. Yeah. So will there be impact on other metrics? Efficiency, I think it depends how you relate to efficiency. If it's performance, of course, yeah. Or you can say overall system performance, then also timing delays. I think again it's timing delays, I would say is related to performance, right. It's like if one of the core wanted to have higher frequency but it cannot, then it's going to run at lower, yeah, and this will impact the timing of the applications, and that is why that will result into like lower performance, yeah. Reliability, that could be interesting one. So you know, like this trojan can cause some reliability issues as well, yeah, because it's just sitting in the middle and doing something extra unnecessarily, right. That means using part of the chip more and more, yeah. So it can basically do some kind of you can say like heating of the chip, or something else. Yeah, so it can make the whole system less reliable. Yeah. Okay. So heating, I think we covered. Setup and hold violations. Yeah. So it's going to violate. Yeah, like what you want to do. I don't know what you mean by setup and hold. Yeah, you're not sure about it. So communication cost and computation cost. So communication cost is like, again, the requests are being modified, right? So it could be like when the request is modified, the number of bits in the packet change. Yeah, could be, but we have not evaluated that. Yeah, so it could be it can cause more communications. Yeah, okay. So make the chip lifespan shorter. Again, this one is related to like if the chip is operating at higher temperature. Yeah, if there's a lot of heat in the chip, so that will make the whole chip basically to fail as quickly as possible. Yeah, okay. So this is possible. Yeah, but in our work we have not evaluated all the things. Yeah, but you can think like these Trojans can have these kind of impacts as well. Okay. Yeah, good. Okay, we saw this one. Okay, so any questions on the Trojan part? Yeah, I think I missed to mention the paper. So we have a paper in a journal and in a conference as well that has evaluated all these. Yeah, I think you can look on my website. Yeah, I think I don't see here including it. Yeah, questions?
Like the hardware Trojan, in hardware Trojan, like the hardware is different, or
So,
like it is programmed differently.
so you know you when you build the hardware, you just specify like how many transistors and all those you need a different place. So Trojans are just kind of a circuit that is designed in a way it's going to trigger at some point when the maybe that part is used maybe after 1 year or something. Yeah, so it is designed in a way like it waits maybe for some cycle counter. Yeah, or some timing. It doesn't do anything until certain point, but then it triggers at some point, and then
There is no way like it is smart because it is only hardware. No software programming is done.
yeah, so it's mainly hardware. Yeah, yeah. So I don't know if you know, like the lot of fighter planes. Yeah, sometimes aeroplanes they have just crashed or disappeared. Yeah, so some people believe it's as a result of hardware Trojan. Yeah, maybe fighter plane was used for 5 years, but then someone put these Trojans in a way it will trigger after this much of time. Yeah, so there could be many ways to trigger it. Yeah, so there's a circuit that will trigger at certain situations. Yeah, maybe after 1 year, or maybe when the temperature of the chip rises this much, and these cannot be detected in the typical testing when the chip is produced. Yeah, yeah. So this is like just kind of circuit designed in a way that will work not now but rather after some point. Okay. Any other question? Yeah. And the fear is like, you know, like I said, why they are coming into picture. It's huge supply chain issue, right? If countries want to do war, yeah, they might sell some electronics to some other country that might be used in some critical systems, yeah, or defense system, and they may implant this hardware Trojan, and at some point this whole system can go down. Yeah, that is why you can see like every country now wants their own manufacturing, semiconductor manufacturing place. Yeah, they don't want to rely on anybody else. Okay. Yeah, good. So if you remember, another one we said is we are going to look is Just give me a second. Oops. Another one we said is covert channel attack. Yeah, you remember I said you can covertly leak some physical properties. Okay, and I said we will look some of them. Yeah, like how you can leak temperature to get some sensitive information, how you can use sound to get sensitive information, and how you can use timing to get sensitive information. Okay, so first of all, let's look thermal covert channel. Yeah, so as the name says, it is temperature. Yeah, temperature or thermal means heat. So this one uses heat as a media to secretly leak information. Okay, so how it is done? So there is a transmitter, yeah, that will send the sensitive data via the heat. So that means like it could be like something is happening in my laptop, but there could be another receiver here that has a temperature sensor. So if my laptop becomes hot, this receiver will read its own thermal sensor, but then it's kind of guessing what exactly is happening in the next device. Okay, so here then the receiver records the temperature by reading its own thermal sensor and decodes the signal to recover the original data. Okay, so now let's look at example. So you can see like this is a chip. Yeah, so nowadays some of the chips are designed in a way like half of the chip or part of the chip is called secure zone and rest is non-secure zone. Yeah, and nobody wants anything to be transmitted from the secure zone to the non-secure zone. Yeah, so typically this one has separate memory, nobody can see, this one has separate memory. Yeah, but covert channel is a way, or thermal covert channel is a way you can still leak the information. Yeah, so what you can do, maybe you can put an extra program here. Yeah, just a software that can increase or decrease the temperature. Yeah, and maybe there is a password store. Yeah, in some binary format, and if it's like 0, you can have some temperature. If it is 1, you can have some temperature. Yeah, but how this typically happens? So like let's say at core B at the receiver, you are receiving this kind of temperature. Yeah, there is no change in the temperature, and then it goes up and comes down. There is a change in the temperature, and then there is no change. So no change can be bit 0, and the change can be bit 1. Yeah, so now think there can be a program on this. Yeah, it does nothing for some time, then it does extra load, it increases the temperature, and then temperature comes down. Yeah, then it does nothing. Yeah, so this kind of pattern can be created, and because this one is becoming heated, because they are very close, right, the sensor on this one will have some kind of similar properties. Yeah, so the temperature will fluctuate on that one in the similar way because they are very close to each other. Okay, and then from that information and that fluctuation in the temperature, you can decode something. Yeah, so in the literature, if you will see like these kind of things have been used, and you can decode around like 5 bits per second. Yeah, but if there are sensors that are, you can say, more fine grained, then up to 20 bits per second can be transferred. Yeah, hope you get the idea. Yeah, so this is just temperature, but you are doing some encoding of the temperature to get the information. Okay,
So what kind of temperature sensors are used in this?
in each laptop, each phone, we have a sensor. Yeah, but this one is assuming you have a sensor here, you have a sensor here as well. Yeah, so these are typical sensors. Yeah, we have in each of them. Okay, yeah. So I think one of the reason you might have seen like maybe you have seen some army people or defense people, right? You can see their laptop, it's not like very thin. Yeah, it's very thick laptop. So in the past it has been like those laptops are doing something, some people have put some receivers next to it to get its like what kind of power profile it has, what kind of temperature profile it has, what kind of electromagnetic radiations it has, and then from that receiver they can really guess what exactly is happening. Yeah, that is why these are made thick, so that by the time the temperature or power reaches the receiver, its magnitude is very, very low, so you cannot get anything. So this covert leakage has kind of happened in some defense places. That's why people put it so big. Yeah, so no, nothing can be detected. Yeah, okay, good. I don't know, it's a kind of hidden because we changed the slide mode, and this is very active research topic. Yeah. Okay, so now how we can detect that? Yeah, so if something like that happened, yeah, so if you want to stop it, the first thing you have to do is detect it, right? I don't know when we were supposed to stop, have the break. 11, right? Yeah, we can keep going. So detecting, again, there can be many ways. So this is one of the approach that was developed in my group. So what we have, you have the system, right, with many cores. Yeah, and this temperature activity is happening on all the cores. Yeah, so what you can do, you can collect temperature of all the cores. Yeah, so it's like core 1, you have like y-axis temperature, x-axis time. Yeah, it's like varying maybe this way. Yeah, and it's going up and down on core B like that. So all those temperature values over the time on x-axis for each core, you can do some kind of scanning, and this one is actually called online frequency scanning. Yeah, so it's like that temperature you convert into the frequency domain. Yeah, and when you convert into frequency domain, so you will find like there is some spike at certain frequency, because that's the kind of frequency at which the temperature is being transmitted. Okay, later on we are going to see some kind of this graph that I said. Yeah, it will be more clear, but the main thing is you keep collecting the temperature like every second, every second, every second, every second on each core, transform that into frequency domain, and now again frequency domain is like there is like many frequencies. Yeah, and there is amplitude of the signal, and then you keep scanning it like with some window size, and at some window you will find there is high amplitude. So if you find that kind of amplitude, you can potentially say there is an attack or there is information being transferred at that frequency. Okay, so like I said, this is processed with a band pass filter in the frequency domain, and this is like linear scanning band B. So again, in the at different frequency there is different amplitude, so this band pass filter is just shifted from left to right. Okay, there is some center frequency, there is some bandwidth. Okay, there is also some frequency increment, like at what speed this window will slide from left to right. Okay, now like I said, in the frequency domain, if maximum amplitude at certain point is greater than the threshold, you can set again some threshold. Yeah, like what should be the amplitude. It's more than that, that means you can say there is a thermal covered channel. Okay, yeah, okay, so there are more details in this paper. Yeah, so this one is about countermeasure against thermal covered channel attacks. So now here we have seen how it can be detected. Yeah, in a bit we will also see like how this can be stopped. Yeah, so once you have detected, stopping might be easy. Yeah, detection is the most difficult part. Okay, okay, I think I have a question now. Let's go there. Okay, so we used in the previous example temperatures. Yeah, on each core every second temperature profile be transformed into frequency domain and did this scanning. Yeah, so can you think of any other metric or any other parameters apart from temperature that can be used? So this one we get temperature of each core, right? Okay, electromagnetic radiation, yeah, that's good one. You can think of getting electromagnetic radiation of each core. It might be difficult to get, but you need some kind of then sensor on each core, right? Electromagnetic radiation is easy to get for the whole chip, yeah. Again, temperature is also easy to get for the whole chip, but then you need sensors for each of the cores, okay. Change in magnetic field, okay, interesting one. Maybe there is a way, each core has different level of magnetic field, yeah, but I don't know how this this one will work, yeah. If something is executing on some core, well will there be a magnetic field, yeah. So I'm not sure about this one, yeah, if there will be any magnetic field, yeah. I mean, another thing could be, you can simply think of the power, right? What is the power of each core, yeah? So over the time, what is the power level? Because if you look temperature, it's mainly related to power, right? If it's high power, high temperature. So you can also look the power values, okay? There could be lots of other things you may potentially use, yeah? You can also say like, what is maybe the utilization of each core, yeah. So over the time, maybe 90%, 100%, 80%, something like that, yeah. Now if you transform that to frequency domain, it might be you can find like at certain frequency there is high amplitude, yeah, which means there was a point in the processor something drastically happened, yeah, the temperature was increased, right, then you can basically get it. Okay. We have seen this one, we have seen this one. Okay, so now let me tell you, just a second, I think it's loading. Okay, so we developed another system. So now here you can see we are not using temperatures, yeah, we are using IPC value. So it's like instructions per cycle, yeah. So this is very kind of useful metric, yeah. So you can imagine if there is a lot happening, the number of instructions that will be processed per cycle on each core will be a lot, yeah. If less happening, it will be less. Same like temperature, yeah, if it's a lot happening, temperature change will be a lot. So similarly, like to temperature, we used instructions per cycle, and then also we can detect, yeah, okay. Okay, any questions? No? Okay, now let's look the defense, how you can stop it, okay. So here again, this one we are saying it's called like DVFS based traffic blocking, okay. So DVFS means dynamic voltage and frequency scaling, okay. So you basically make the frequency up or down, and in that process you can block it, yeah. So now let's say like this is the signal code that you want to transfer, yeah, with the help of the temperature, like 1010, yeah. You remember, if we want something like this, so we want some profile like this, right? If it is 1, change in the temperature. If it is 0, no change in the temperature. If it is again 1, change in the temperature. If it is 0, no change in the temperature, okay. And this profile we are getting typically with normal frequency label, yeah. Like I said, how you can do, you can put some extra program in the transmitter, and that can just use more of the CPUs or cores, and it can increase, okay. So this is the normal frequency level, yeah. And now let's assume like normal frequency level is somewhere here, yeah, okay. So if you are operating at that normal frequency level, you will get this kind of profile, right. But when you are operating like, let's say here, let's change the normal frequency level to some low level, yeah, that is called dynamic voltage frequency scaling. So you were at normal, but you change it to the low level. Again, you went to normal, but change it to the low level. So you can't keep changing the frequencies. Yeah. If you keep doing this, you can see like with rise in frequency, there will be typically rise in temperature, but with low, this temperature will not reach until that point. Yeah. It will start dropping much early. So you may get some profile like this. Yeah. Because it's fluctuating up and down. So if it's always at up, temperature keeps increasing. Yeah. But now because you are coming at lower frequency, you will get some profile like this. Yeah. So now from here, you can see like it's not easy to get the information in that kind of format. Yeah. Because the temperature profile is more or less the flat. Okay. So now in essence, you can think of like you are getting the information with the change in the temperature, right? If you can make the temperature always the same, yeah, that means everybody has to assume it's always all 0 or all 1. Nobody can get any information. Yeah. So with this one, we are doing up and down. Yeah. That's why it's like more flat. Yeah. So it's kind of not easy to deduce the information from this. Okay. So again, with any side channel attack, like temperature, if it's power or anything else, people are getting information from it because it's increasing or decreasing. Yeah. And people are having some decoding mechanisms. So if you can ensure my electronics always runs on the same temperature, same power, no side channel attack can happen. Yeah. And that's what this one is trying to do. Okay. Yeah. So if something like this you are doing, now you can see like you are from normal frequency level, you are coming to low frequency level, right? So now when you go to low frequency level, you are also impacting the performance of the application that will be running on that core. Yeah. So here you get some security, but you have to get some penalty in terms of the performance. Yeah. So that is why we say each defense mechanisms has its trade-off, right? If it's the best defense, it may be heavy, use a lot of process, but then it may impact the performance, yeah, because there is a lot of extra process. Yeah. Also there could be more energy consumption or something like that. Okay.
So this frequency that we are changing is like the power input to the core.
Yeah. So typically in processors we change only the frequency. Yeah. This is kind of matched to a power level. Yeah. There are like 20 or 30 frequency levels. You change from one to one, another, and then it says it goes from one power level to another power level. Okay. So this is one defense. Yeah. Changing simply the frequencies. Okay. All right. Any more question on this? Okay. Now let's look some results. Yeah. So like I said, yeah, you have to record temperature over the time. Yeah. This is how it will look like. Yeah. And now this is like basically without DVFS. Yeah. We are not changing the frequency. It's just at the normal operating frequency. If this signal is transformed into frequency domain, it will look something like this. Yeah. It's like some amplitude at different frequencies. Yeah. So remember I said you can use a band pass filter, you can keep scanning, and if at certain frequency the amplitude is more than a threshold, you can say maybe if it's more than 0.02, you can say there is an attack. Yeah. So now this is without DVFS. So with DVFS, you can see the temperature profile will be more zigzag, yeah, or more flat. Yeah. You see like in the previous one, yeah, it was going up down, but at the bottom it was more flat. Okay. So with some real applications on the platform, the temperature became like this. Yeah. From this to this one. So similarly, if you transform this one into frequency domain, you get this kind of profile. So you can see here there is no higher amplitude. Yeah. So here you can see like essentially the information is transferred from the source to the destination or the transmitter to the receiver, but this information is not very useful. Yeah, so it's like attack is still happening, but attacker is not getting any useful information. Yeah, so there is a metric called bit error rate. Yeah, so if an attacker is getting all the information perfectly fine, yeah, let's say 100 bits he has to get. If he gets all of them, that means there is no bit error rate. Yeah, he gets all the information. But as a result of this, it might be like he just gets only 10% of the information. Yeah, then bit error rate is like 90%. Yeah, because there's so much error in the data that the attacker gets. So now here, if you see, if there is no DVFS, the bit error rate is very, very low. That means attacker is able to get most of the information or most of the bits. Yeah, maybe out of 100 he can get for like 90 bits correct. But with this one, he is still going to use these decoding mechanisms, but the decoding results will have very high bit error rate. So it's, I think, around 96 or 97%. Yeah, so only 3% bits are correct. So this information is not very useful for the attacker. Yeah. Okay. Okay, so I have again a question, and I think with this one we will also stop for the break. Yeah. Okay, so can you think of other methods and controls than frequency scaling? Yeah, so you saw we did this dynamic voltage and frequency scaling, right, to make the temperature as flat as possible. But can you think of anything else? So the main aim is, like I said, yeah, making this temperature profile as constant as possible. So basically you have to think of like what kind of controls you can have in your processor. Yeah, or you can think from a different angle, what kind of things you can do from software point of view. Yeah, there could be some hardware control that you can change to keep the temperature almost the same always, or you can think from software point of view. Yeah, can there be any help from the software? Okay, so reduce the size of the capacitor in the chip. Okay, I need to think a little bit. So capacitor is typically for storing, right? Storing energy. If you reduce the size, there will be less and less energy, less power. Yeah, could be a way. Yeah, so it's like, you know, in the previous example we saw like there's different power request for different cores. Yeah, so there's different frequency level. So if it's, let's say, all the cores are almost running at very kind of in the very minimal range of frequencies. Yeah, so we changed from normal to low, right? But if that low is not at all available, yeah, because there is no power or no capacitor for it. So if the range is very low, you can't really do anything, right? Maybe even if you change, but temperature profile might be the same. Yeah, so it's like you are running at 2 gigahertz, but if you change to 1.9 gigahertz, maybe it is the same. Yeah, but from 2, so let's say you are going 1 gigahertz, then temperature changes a lot. Yeah, yeah, that's nice idea. So basically you can limit the number of frequency labels or power labels to kind of with some minimum range. Yeah, but you can see with that you can get some security, right? Because nobody can get this information. But then again there will be penalty in terms of energy consumption. Yeah, so why we have this so many frequency labels? It's because if not a lot of things are happening on the processor, we want to reduce the frequency to very low level. Yeah, and if something is happening, we want to increase. Yeah, so you can see like by limiting this range maybe to very small, we can get the difference. Basically the temperature fluctuations cannot be a lot, but then we cannot save energy. Yeah. So that's what we always say. Yeah? There is always a trade-off. Yeah. You get security, but then you pay in terms of some other metric. Okay. Anything else you can think of? Let's have a break, and we discuss more options. Yeah. After this, in half an hour. Yeah. Okay. And another thing is, like, here we are talking mainly in terms of computing, right? But if you are working in some slightly different field, you can think of the same other places as well, right? So because I am into like computing, yeah, so that's why my work is around that line, but you can apply similar concepts many other places. Yeah, for example, this covert channel, it came from communications domain. It was not into computing domain previously. So similarly, one concept from one place can go to other place. Okay. Okay, break, half an hour.